assignment really decimated this.
No, tomorrow is actually operating system, midterm exam plus artificial intelligence exam. So basically people...
What? Oh.
Tomorrow, yeah.
Oh, the operating systems midterm was today and AI.
No, tomorrow.
Tomorrow.
Both
AI.
are both are tomorrow.
They're both tomorrow. Yeah.
There are 2 exams.
So in the future, so in the past roughly 24 hours, I got a few requests to move the homework deadline. If people had asked me like earlier, like a week or 2 earlier, I would have happily moved it, but I didn't want to move it in the last 24 hours. Then every deadline people ask me to move it, and it's not fair for the people who actually took the time and made sure they got it done ahead of time. So I was able to move that one, but if it happens again that there's something due on like right before some midterms, please let me know, but let me know ahead of time, and we can adjust this stuff. Probably the people who are most affected are not here, so if you're watching on the video, you can let me know. So, all right, so since the last class before spring break, yeah, I'm probably as excited as you are. So, just keep in mind that the project intermediate report is due on Wednesday, and try and get what you can done so I can give you some feedback on how to finish that up. Right, so that should be your goal. I'll kind of go through in detail what I'm looking for on Monday. I'm sure most of you don't want to think about it right now, but you can read it in the document. So we're still in regression, and today I'm just going to cover the SVD and PCA. And so I'm guessing probably people have heard of these things. They've probably seen them before in the classes. So I'm hoping to accomplish a few things. One is to kind of give a different view on these topics than hopefully you've seen before, kind of a more geometric view of this. And so hopefully this provides some nice intuition. And also the SVD and PCA, and they're a bunch of related things. And in the literature, you see that they're often kind of confused exactly what they're doing. So I'm going to try and be precise and kind of I'll try and see how these things relate to each other. So who's heard of the SVD before? So who's not heard of the SVD? Okay, so who's heard of who's heard of PCA? And who's not heard of PCA? Okay, that's not so bad. So it seemed that most people had either heard of one or the other, but maybe not both. They're pretty much the same thing. They're not. The SVD is a linear algebra operation, and it basically solves the PCA, but you have to do a little bit else to really solve it. If you don't do it quite right, you're not going to get exactly the right solution, but you get something close. All right, so before we go any further, let's review. Just remember we're talking about regression, and so to draw another picture in 2D, just to remind you, you're going to have something like some points, and we'll think about linear regression, and then the goal is to find some line that best fits these points. And we had talked about how if you usually do least squares linear regression, usually that means you're looking at this vertical distance. It's going to look at all these distances here. But what we're going to be talking about in the lecture today is actually looking at this projection distance, where you are minimizing the sum of the square of all the distances to the closest point. So if I draw one kind of point out here, So if I do least squares linear regression, what I'm doing is so this is what the view of the residual looks like for least squares linear regression, which is a standard thing. If you're doing PCA, and I'll write down the formula for this precisely, so you're mapping onto the closest point. So this is going to be a right angle. Okay, so this seems a little bit tricky because you need to be a right angle, but I haven't defined what this blue line is. I haven't defined the slope. So I need to kind of find this line while minimizing these residuals based on this right angle. And how do we actually calculate this, this residual? This is the difference in the y-coordinates. This is going to be a little bit trickier, right? Okay, so this is the residual when you're doing PCA. Okay, so so it seems like maybe doing this one is maybe always better, right? You always would want to minimize the distance to the closest point instead of this vertical distance, right? So when would you not want to do that? So remember that in linear regression we had these x coordinates, and this could be like, it could be one value, or it could be like a high dimensional points, and then we had these py coordinates, right? And these were what we're measuring the error on. So this was for least squares on linear regression. For PCA, we're not just measuring in this y-coordinate, we're measuring in this distance, which has to do with whatever these x-coordinates are, as well as this y-coordinate. So why would that be bad? Maybe. Yeah.
Maybe if you're using your estimated function to predict future values.
So let's give an example. So let's say that these x-coordinates are people's these are people's height, and this is their income. Okay, so I believe this may actually be true, that there is some correlation between the height. The taller you are, you tend to make more money. It's unfair as it is. Even if that's not true, let's say that we had data that said that looked kind of like this. Okay? So what is this least squares linear regression measuring here? It's saying that this is a person, and we know their height, and we know their income. And so this is the error. We're predicting, given their height, we're predicting what their income is. Right? Now let's say we have a height and an income, and if this is the residual line here, then our estimation is here instead of up here. Okay, so now I'm minimizing this distance. Well, this distance now, here it was strictly an error in the income. I can measure this as dollars, right? This distance is, well, I'm not sure what the units of this distance are, right? In the x-coordinate, it's height, so maybe that's inches. In the y-coordinate, it's dollars. Oh wait, maybe it's not inches, maybe this is in centimeters. If it's in centimeters, then this is a scaling, and this line would actually be different. If it's in centimeters instead of inches, then these points are even more spread out. So I'm actually going to get a different projection if I scale this, which is kind of weird. So if you don't have the same coordinates, if you don't have the same units in all of your values, you probably don't want to use PCA. You're going to be doing something kind of screwy. You're messing up with the units. if you're doing least squares linear regression, the reason you're doing this vertical thing is because you have some possible unit that you're trying to optimize, and it's with respect to these other things, and if you scale them in a different way, you're still measuring the difference in the dollar amount of income. So if you want to use PCA, you need some data set that somehow has the same units everywhere. Okay, and so some examples of where you may get something with the same units. So one example where this is used is in if you're looking at images, right? So I gave this example earlier of these SIP features, where you took this image and you kind of found the special points on the images, and then you kind of lifted these to a high-dimensional space. And yeah, you can kind of do this, but you can do images in this other way where you have a bunch of these pixels, and you kind of, every image is maybe, let's say you have an image of a face, and this works well if you have every face is kind of centered in the image, and they're all like 1,000 by 1,000 pixels. Then you have 1,000 by 1,000 coordinates, and each one is a value in black and white. They're all the same units. And then it kind of makes sense to use this PCA. They're all the same units. And we'll talk about what's actually going on when you're doing that a little bit later. But you can have some other things where you're measuring say some temperature values from different sites or at different times of the year. All of these are temperature values, and you want to see how these values vary together. Which ways are they most likely to vary? Okay, and so that's what this PCA is going to give you. It's not going to, and then you can kind of, so as we'll see, that you'll get the main variation, and the rest you can think of as kind of noise. And that's kind of what's going on here. The linear regression in this way as well is also giving you the main correlation, and then the rest of these residuals are the noise that you kind of want to say, let's ignore those residuals. But the PCA works kind of, it's explaining how different coordinates vary in the same way, whereas regression is kind of trying to predict these things. Okay, so it's important to keep this straight. So there's some people who work in, what is this? There's artificial intelligence, a modern approach, right? So if you're taking the AI class, I'm not sure if this is the book you're using, but I think they don't talk about PCA. I think that book doesn't cover PCA at all. And I've heard that the reason was that people too often make this mistake of trying to apply it when the coordinates have different units, and they shouldn't do it. And he just decided we're just not going to cover it in the book. But it's a really useful thing in these large data sets, say, that you find on the internet, where you're looking at, so say you're looking at customer reviews of books and stuff. Every book is like one of these coordinates, and every customer is providing these readings, and they're all the same units. And this kind of tells you how to group these together in a different way. So there's a lot of new applications which are really using PCA a lot. So it's really worth kind of understanding what's going on. And that book is called AI, the Modern Approach, but it was now written over 10 years ago, I guess. And I'm not sure, if it's still modern or not. It's always a strange choice of the title. Okay, so let's try to define this a bit more formally. So the input is going to be we're going to think of it as a point set, P, and this is in RD, and so the size of the point set is going to be N. So how you can think of this as P, you could also think of this as a matrix. So this is the first, so there are these different points up to Pn, and each point is going to have these D coordinates, so P1, 1, P1, 2, up to P1, D. And so then this is P21, P22, P2D, and so forth up to Pn. Right, so you can think of this point set as this matrix where this is the ith coordinate is the ith column, and the jth point is the jth row. Okay? Now, what you want to do is to find a subspace. Switch this. So the goal is a subspace F, which is going to be in Rk. So it's actually, so this is going to be, so this is equal to Rk, or you can think of it as it's a subspace of Rk. It's a k-dimensional subspace, right? So this is a one-dimensional subspace. If you're in 3D, you can think of like a plane as a two-dimensional subspace, and in higher dimensions, you can think of a k-dimensional subspace for some value k, where hopefully you're going to think of k is going to be much less than d. So in some cases, you want to do this where k is 2, so you can take the points and draw them in the plane. And we'll talk about this. And in fact, the subspace is going to define a function where this function mu maps from Rd to F. So, and how it works is these points, so here, F would be this blue line here. This would be F. And so we're in R2, these points are in R2, and it maps to the closest point. So this function mu is going to be this mapping of these residuals onto the subspace F. Okay, so so mu of x is equal to the arg in of y in F of x minus y. And so if I don't write the norm again, this is always the 2 norm. This is the straight line Euclidean distance. Okay. So we can define this function even if we don't know what this subspace is. Maybe you can write this as mu of f. And so then the goal, so we want to find the subspace. So we want to output f, which is the arg min of f of okay, so we're going to minimize the sum of the squared distances again. And the reason this is the sum of the squared distance is because it's, the math works out easily. You can try and do this for sum of distances, and it's going to be a harder problem computationally to solve. Okay, so we want to find this subspace, this k-dimensional subspace, that minimizes the sum of these squared distances. So it's very similar to the least squares linear regression, except we're doing this projection distance instead of the vertical distance. And so this is basically the goal of PCA. You can actually say a little bit more about these subspaces in addition to just the subspace F. We're going to break it down in a hierarchy, say this is the most important direction, the next most important direction. We'll try and understand what the subspace means a little bit better if you're not used to high-dimensional stuff. Okay, so how do we solve this problem? Okay, so how do we find the subspace? So before we could do this matrix operation with the key thing was this matrix inverse, and we could automatically pop this out. Now we're going to do this with instead using the SVD, which is another matrix operation. SVD is the singular value decomposition. Okay, and so what it's going to do is to take as input a matrix, which might be this matrix P, and it's going to output some U, S, V. So and you can just call this in many any language that has linear algebra support. You can call this function. So we'll do some experiments in MATLAB, which is probably the most optimized language. There's lots of special ways to do this. There are various ways to do it. If the matrix is more sparse, you want to call a different algorithm. And MATLAB kind of automatically detects what's going on and calls the right version. If you call this, you can call, all of it goes back to these libraries that are written in Fortran. So this operation, it doesn't matter what language you call it in. It's going to run the same base code, although MATLAB may choose a different version of the algorithm anyways. But the actual code is implemented in Fortran, so it doesn't matter that MATLAB is say slow. But there are packages, you can download packages in C directly called the Fortran libraries, or some stuff on top of them, and many other languages have built-in functionality for doing this. Okay, so the goal for this lecture now is I'm going to explain what this decomposition is. It's going to be a set of these three matrices, basically, such that P is equal to U times S times V transpose. So it's a decomposition of P into three matrices. So I'll explain what these mean, and then in addition, this will explain how to get this PCA and how to get more information. We're also going to try and relate this to, so first of all, PCA. Second is the eigendecomposition. So we talked about this earlier for the spectral clustering as well, and this is very related to SVD, as well as something called MDS, which is multidimensional scaling. This one is very often confused what this is actually doing. When people say MDS, they usually mean calling some version of PCA, but they'll write down, when they try and write this down formally, they'll say something else. Like if you look at the Wikipedia page for MDS, it's actually wrong. I don't know, it's got some weird stuff on there. But this is very much used to kind of get an embedding of a distance matrix. So we'll talk about how all these things are related. Okay. So, and at the same time, I'll go through a running example here. So I've got a version of Octave running here, and I've got in a matrix P, and I'll use this simple example, and I'm keeping it pretty simple because it's going to let me draw it on the board. Okay, so this is so this matrix P is now it's an n by d matrix. So that's going to make it 4 by 2. And so each of these you can think of as points, right? So the first one is coordinates 4, 3. So it's going to be around here. So this is P1. 2, 2 is going to be, say, this is P2. P3 is about -1, -3. And P4 is -5, -5, -2. And so as we'll see later, there's some special property about why I picked these points. Okay, so the first thing you can do is you can call So you call the SVD, and what it gives you are these three matrices that are coming up: U, S, and V. Okay, so you're going to get these matrices, and I'll start with U and then talk about V, and I'll start with S and start talking about V and U. So S is going to be it's going to be N by D, and it's is going to be diagonal, and so that means that it only has things on the diagonal, but it's not square, so where the part that's not square is just all zeros. So you can actually before I do this, you can write this as a picture. So you can think of this as 2 columns and 4 rows, so it's going to look like this. And I said before, it's going to be U times S times V transpose. So U is now going to be an N by N matrix. So this is P, this is U, this is N by N. This is going to be S. So it's going to be have the stuff along here. All of this will be 0, and all of this down here is S. All of this is 0. And then you're going to have V. Actually, you can have V transpose. And so so this is V transpose. So this is going to be N times D, and so V is going to be D times N. Okay, and so both these are going to be dense. This one is pretty empty. Okay, now so you're going to have certain properties of these two matrices. They're both going to be what's called orthogonal, which means that if you take any row of, so if I take any two, actually, if I take any 2 columns, C1 and C2, which are columns of U or V, so of just U, or of the columns of V, then C1, then the dot product of C1 and C2 are going to be equal to 0. So this means that the columns are orthogonal to each other. So you can think of C1 like this and C2 like this. So in V, the columns are going to be living in are going to be d-dimensional columns. So these are going to be d-dimensional vectors. In U, they're going to be n-dimensional vectors. Okay, and I think generally the ones from V are going to be more interesting if we think of them as points, and the dimensions are kind of attributes of the points, right? So for thinking these images, each row is an image, and each column is the value of the same pixel in every image. So then you're going to have that these are orthogonal, and really what that means is that they're doing some sort of rotation. So they're so it's not, if you know the mathematics behind it, it's not exactly rotation. It may also do like a mirror flip. So if it's just a rotation, they're called special orthogonal. But so these could be doing a mirror flip, but basically it's taking data and it's kind of rotating the data. So for V, this is a N by D matrix. It's sorry, this is wrong. This is, in order for them to be orthogonal, they have to be square. So this is a D by D matrix. Sorry. So for V, it's rotating it inside this d-dimensional space. So you're thinking of points, a vector in a d-dimensional space, and you rotate it to someplace else. Okay, so this seems kind of abstract, so I'm going to try and go through some picture. So initially, we're going to keep with this two-dimensional view of things, and we're going to think that this is coordinate x1, and this is x2. Okay, and so if I have this matrix V, then each of the rows, I'm going to have, if it's d by d, that's 2 by 2. That means I can have 2 of these columns in V. These columns are going to be, are going to represent these two vectors which are orthogonal to each other. And so if I look at these vectors, I'm going to get V1 is going to look, so let's look at my matrix V. So V1 is going to be pointing -8 and -0.5, right? So it's going to be roughly about here. So these columns are also going to be unit vectors, right? So also any column in U or V is going to have just one. So this is going to be V1, and then V2 is going to be pointing up in this direction. Is going to be orthogonal. So its x coordinate is going to be see, it's going to be about 0.5 and about point.
The first one, the y next to right?
Yeah, no, I'm drawing. Got this transpose somehow. So minus. I think that. So I think I actually want. Let me do this. So I have this vector x I'm going to consider, and I have VT, which is V transpose, and I'm going to do VT. That's going to give me minus. So. Okay, well let's draw what's up here. So I'm saying the column, so that means the x coordinate here. So the first one should have had x coordinate of -8. Okay, and then this one has x coordinate of 5 and y coordinate of -8. So it's going to be roughly down here. And so these should be orthogonal. These should have a right angle here. Okay, and so also since they're on the, since these are on, I haven't drawn these to scale actually. They should have actually been shorter, but if they're length 1, they must be on this. They must point on this unit circle. So so they should have actually been shrunk compared to these points, but we'll see that in a little bit. So now if I can think of taking some vector x here, and so now if I multiply, so what I'm going to do is I'm going to look through what happens when I do p times x, where x is some vector, and in this case I'll use where x is x is a unit vector here. So actually I want to use v. I think I want to use v transpose. So I want this vector up here. Yeah. So I'm going to multiply first by v. So I'm going to look at several things here where I'm going to go V transpose X. Then I'm going to look at what happens when you do VS, V transpose X, and then U times S times V transpose X. And this will be equal to PS because this equals P. And you'll see that it's going to rotate the space, it's going to stretch it, and then it's going to kind of rotate it again. Okay, so I'm multiplying by V transpose, and if I take, let's see, if I take V transpose, I get this matrix here instead, and now that's going to have columns that look somehow want V1 to be pointing. Okay, so it turns out it doesn't matter so much what direction V2 is pointing. I think what happened is the choice of the sign on these vectors is actually arbitrary, and I have in my notes when the sign was chosen differently for whatever reason. So okay, so let's go ahead with this example. The notes are going to have this one flipped, and so it's not going to matter so much. Okay, so if I take this X and I project it onto V1. So if I take, when I'm multiplying X by this matrix V transpose, I'm essentially projected on each of these coordinates, and this is like taking a dot product between X and the vector V1, and so I get a location here, and this is going to be something inside this unit circle, and then I do the same thing on V2, and I get a projection here. Okay? So what this rotation has done actually is that it's transformed my data point X into a coordinate space described by V1 and V2 here. So what I can do is I can draw a new coordinate space, V1, V2, and now I can map this point V. We're going to call this this value here, we'll call this Y. Now Y is going to live in this coordinate space. So let's see, on V1 I'm getting about here, and this is going to be about 0.8 up here. And it's on V2 it's going to be minus 0.8. And on V2 it's minus about 0.5. So this is now going to be the point Y. I have a new coordinate space based on these coordinates. Because these are orthogonal, they describe a coordinate space just like x1 and x2 describe a coordinate space. So that's what I've done here. I've transferred this to a new